Sorting algorithms. Sorting is a really important thing in computer science, and there are many different ways of doing it, and we're going to take into account the notion of performance. Sorts can take a long while. We want to start looking at what's faster than what. This is just an introduction. Some other references are listed here in the notes, but this is basics stuff and good examples of using various techniques with our loops and arrays. One basic thing that's going to be underneath all of our sorts is swapping or exchanging elements within our array data, and we're going to say which two elements to swap by their index, so we can swap the data at index m and n. And you might think, to start off with this line, well, we want the contents of data n in data m. The problem is that this clobbers the old data in data m. We lose it, and we can't put it anywhere else. So it's important that we first access data m and remember it in another variable. Then, after we've used the contents of data n, we can reassign data n from the value that we remembered. We need this extra temporary variable. I'm going to let you read about bubble sort if you like. It's something of historical interest but not efficient. But in this section we include the idea of inversions. If we look at two indices in the array like 7 and 16, 7 is before 16. If the array were sorted, then this would be less than or equal to the one further down the array. Backwards here means we have an inversion, two elements that are out of the right relationship with each other. What we're going to do is then modify the array and move things, ultimately reducing the number of inversions down to 0. We can calculate easily the maximum number of inversions in a list. If you have all the data in the exactly opposite order from what you want, all pairs are inverted, and you can calculate the total number of pairs that are inverted. And we will see several sorts that exchange only adjacent elements, eliminating only one inversion at a time. So like bubble sort, they must be order of n squared, because we've got an n and another factor involving n here. Here's a slightly different sort. The idea here is to go through the array and pick out the minimum element, or actually the location of the minimum element in the array data. In order to make this work through the loop, we need another parameter I, that we're only going to look at elements starting from index I and going later. Initially, I is 0, so we would find the minimum element, or the location of the minimum element, in the entire array. And what we do is we make sure that it ends up, well, in this case, in the 0th position, the very beginning of the array. So after once through this loop, the absolute minimum element is in position 0. That's its final position. We only need to worry about the rest of the array at that time, from I equals 1, that we get the next time through the loop, onward, and we just continue. In this case, we will start looking for the minimum from index 1, because we've already taken care of the final position of the element now at index 0, and we continue swapping the element at the minimum location into the bottom position that we still haven't sorted. And if we go all the way through the list this way, we pick out all the right elements in order to be in the sorted list. Here is the helping method that finds the minimum. We do this incrementally. If you imagine only looking at the start, the minimum position so far is the only place we've considered. And then we start from the next position, start plus 1, and go all the way through to the end of the array. If we find any data that is smaller than what our minimum so far was, then obviously our minimum so far was wrong, and we switch, and the position of the minimum now is where we found this smaller element. If we go all the way through the array this way, we will have found the minimum in the whole array, at least starting again from index start, and we return the location of that smallest element and use it in our main function here. Here, the main thing we're doing is comparisons, but still, every element gets compared to everything else, so we have the same number of comparisons that we had. We always have this maximal number of comparisons, which is certainly order of n squared. We do exchange fewer elements because we just put each element in its final place once. Here's quite a different approach: insertion sort. The idea here is we will build up a longer and longer sorted list from the bottom of the array and gradually add in further and further along elements. For instance, there's nothing to do for the element in the position 0. That single item list is certainly sorted. But we can start looking at the next item at index 1, and we will check for an inversion if the latest element should be further down the list. And if so, we exchange it, and we decrease I, which means we look and see if the number we just exchanged should go even further down the list. So we loop as long as there is a place to put an inverted element. If we reach the bottom of the list, there's no place to go. It must be in position. But otherwise, we check to see if we need to swap it one more time further down the list. Very short code. But again, we're only exchanging side-by-side elements, only removing one inversion at a time. Again, this can be order of n squared in the exchanges, though it may have fewer comparisons than with selection sort. You can read about shell sort, another sort that has relatively short code that is useful when you don't have much memory or have parallel processes going on, but we will skip it here. Briefly want to mention quicksort. This is an advanced sort. We are not really going to go through the details. You can look. There are some comments in here explaining what's going on. But while the previous sorts that I talked about were of order n squared generally, the average behavior of quicksort is order of n log n. That's enormously smaller and more efficient than the previous sorts for a large number of items in the array. However, this is a curious sort in that it is not consistently of that speed. It can, on some occasions, be as slow as insertion or selection sort. It uses the idea of recursion, which we have not discussed. It turns out that we can partition the items into smaller items and larger items with a few of the middle item in the middle, and then go ahead and sort the list in the beginning of the array of the smaller items, and where we have the index higher later in the array, sort in the same fashion, calling the same function we are defining. This is not circular because the size of the data that we're looking here gets smaller and smaller, and eventually this condition ceases to be true. We're down to like one element or none, and so the process does actually stop and is quite efficient. You'll learn more about this if you go on in a data structures course.